welcome back to my system design series. If you are new to this channel or new to this playlist, then let me introduce myself. I am Aarchigandhi, a senior software engineer, and in this playlist, I am covering DDIA books chapter 1 to 12. And as of now, I have completed chapter number 1 to 6 in previous up till lecture number 33. So in this video, I am starting chapter number 7, that is a transaction. So we are covering what is transaction, acid properties, atomicity, consistency, isolation, durability with examples, single node versus distributed transactions, and real world scenarios. So make sure you watch the video at 1.5x or 2x for better experience. Okay, so let's start. Imagine that you are withdrawing money from the ATM or placing an online order. You would not want the ATM to deduct the money from your account without dispensing cash, or an online store to charge your card without creating an order. In the messy real world, many things can go wrong during such processes, but databases provide transactions as a way to guarantee correctness even when failures or concurrent action occurs. A database transaction is a sequence of one or more operations that are executed as a single logical unit of work. All the operations, suppose operation 1 and operation 2, should complete successfully, or none of them will occur. Transactions are useful for maintaining data integrity, especially in the scenarios where there are concurrent users or system failures, by ensuring the system state remains consistent and reliable. Okay, so now let's discuss what is database transaction. A database transaction groups multiple reads and writes actions into indivisible operations. If the entire group of actions succeeds, the transactions can be committed, that is, applying all the changes. But if any part fails or an error occurs, the transaction is rolled back, undoing the partial changes so that database is left as if the transaction never happened. This is all or nothing behavior. This behavior prevents the partial updates that could leave the data in an incorrect state. For example, consider this scenario that there are two persons, Alice and Bob, and consider that Alice is transferring 100 rupees from Alice's bank account to the Bob's bank account. This involves two operations, that is, the 100 rupees from Alice's account and add 100 rupees to Bob's account. Treating this as a single transaction ensures that either both the updates happen or neither any of the update happen. If the crash happens after deducting the Alice account's money, but before crediting the money into the Bob's account, a rollback will reverse the Alice deduction. So no money is lost or credited. From the application's perspective, the two operations A and B are inseparable. They succeed or fail together. Transactions are essential for applications reliability and fault tolerance. By using transactions, developers don't have to manually code for every failures. In a multi-step process, the database ensures that no matter what goes wrong, such as power outages, errors, or concurrent interference, data remains correct and consistent. These guarantees are so fundamental that modern databases implement a set of properties for transactions known as acid properties. A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for each of these properties access the different aspect of reliability. Now let's deep dive in. ACID is the acronym that represents the key properties that ensures the reliable processing of database transactions. Let's break down these ACID properties. First is atomicity. It is also called all or nothing. Atomicity means that the transaction is indivisible unit. Either all the operations, suppose 1, 2, 3 completes successfully, or none of them will occur. In other words, the transaction never ends up doing the partially done. If any part of the transaction fails, for example, 1 and 2 operations are successfully done, but operation number 3 is failed, all the other changes, for example, here operation 2 and operation 1 will be undone, or it will be rolled back, ensuring the database returns to its pre-transaction state. Think of writing an email and then sending it. You would not want the email service to send your half email and then stop. It either sends the entire email to all the recipients or sends nothing at all if there is an error. Similarly, when you withdraw cash from ATM, the machine must either dispense all the cash and debit your account, or do nothing if it can't complete both the steps. You should never be left with the money deducted on your account without receiving the cash in your hand. Okay, so now let's talk about how it is implemented. Database implements Atomicity using a mechanism for transaction rollback. If any of the operation in the transaction cannot be completed, the database engine will undo all the changes made by the particular transaction. This is often achieved through logging techniques. Remember this. From a developer standpoint, you can actually revoke that particular transaction by a command, or rely on the databases to automatically roll back if there are some errors occur. The outcome is that the partial results are never saved. The system state only changes if the transaction succeeds entirely. Okay. Second is consistency, which is also called preserving valid states. Consistency means that a transaction takes the database from one valid state to another valid state, maintaining all predetermined rules, invariants, and constraints of the data. If a transaction would violate any of the integrity rules, such as uniqueness constraint, foreign keys, balance cannot go negative, etc., the transaction would not be allowed to commit. The database ensures that only the valid data according to its rule is saved. In simple terms, consistency guarantees that any data returned to the database as a part of transaction must comply with the rules and constraints. These rules could include data types. For example, the date field must have the valid date. Apart from data type, second is a business rule, such as the account balance must not go below 0. And another is relational constraints. That is, the foreign key must correctly reference to the existing records. So we discussed that it should have the correct data types, business rules, and relational constraints. If a transaction tries to break any of these rules, it will be rolled back and not persisted. That means it won't be saved. For example, imagine a library lending system where a rule says that a member cannot borrow more than 5 books at a time. The consistency principle is like the librarian checking after lending operation that a rule is not broken. If you try to borrow a 6th book while already you have checked out 5 books, the system should prevent the transaction from completing because it violates the library's rule. The library's state should always obey this particular policy. In database terms, the transaction that would let a member to borrow 6th book would be rejected or rolled back to keep the data consistent with the rules. Let's talk about after commit visibility. Consistency in the S-read is sometimes confused with the idea of all the users seeing the latest data. A clearer way to distinguish this is consistency is about internal correctness, that is, adhering all rules at the moment the transaction commits. In distributed systems, consistency also means to have up-to-date copies across all the replicas, but that is a different usage. We will discuss about this in the later topics. Now coming back to this, for example, in one description, when you successfully commit the change, the next time anyone looks at that particular same data, they see valid up-to-date state. This simply means that once the transaction is done, the database doesn't show some partially updated or rule-breaking data. It shows the new consistent state that includes the transactions changes. Okay, so let's move forward. Let's talk about isolation. That is, concurrent transactions don't interfere. Isolation is the property that ensures that the transaction operates as if they were single alone on the database. When multiple, suppose this is a database, and when multiple transactions execute at the same time, isolation guarantees that they do not step on each other's toes. So they will be parallel lines. Think like that. And the partial changes of transaction 1 will not be visible to the transaction 2. And the final outcome is as if the transactions are executed one after another in some order. In practice, isolation is achieved via various concurrency control mechanisms such as locks or multi-versioning that coordinate current transactions. In plain language, isolation means temporary, in progress changes will remain invisible to other transactions until they are committed. Each transaction sees the databases as if it is the only one using at that moment. If two transactions are running concurrently, isolation will prevent them from reading uncommitted changes from each other or else interfering in a way that produces incorrect results. Let's take an example. Imagine two people, suppose this is person 1 and this is person 2, are editing same spreadsheet or same Google Doc. Without isolation, one person might read a value that the other is in middle of changing, which will lead to confusion. This guy will think that I saw the value 50, but after some time it changed to 60. And now my calculation is wrong. With proper isolation, each person will think of that it is their own copy. And only if this person is done with their change and those changes are merged, then only this guy will see these changes. So now as we are discussing about concurrent transaction, let's talk about race conditions and concurrency problems. When isolation is lacking or it is too weak, race conditions can occur in the database. A race condition happens when two or more transactions interleave the operation in a way that the final outcome depends on the timing of those transactions. This will lead to the incorrect or unexpected results. Race conditions are a symptoms of inadequate isolation or poor concurrency control. Let's understand this by taking an example. Imagine this is a document and where inside it the value of x is 100. This is user A and this is user B. Both of them wants to add 1 into 100 and make it 101. Now this user A and user B, suppose this user A have added 1 and made it to the 101. But due to the concurrency, when user B looks at this person looks at the older value of x, that is 100, and it again adds 1 and make it to 101. The final value is 101, but it should have been 102 if both the increments are applied. But this lost update occur because the operations interleaved without proper isolation. With adequate isolation, for example, using locks on the value of x, the second transaction would have to wait or aborted to prevent the race condition. Now this race condition will lead to Anomalies. Let's discuss about them. Some of them are lost updates. As shown in the above example, both the transaction was trying to update the same data based on its initial state. And because of that, one update gets lost. That is overwritten by other. Second is dirty reads. In this, one transaction reads the data written by other transaction that has not yet committed that particular data. If the writing transaction rolls back, this reading transaction have already saw the value which is now not exist. That is that it was never actually saved. It is also called that it is reading or dirty or temporary data. Third is non-repeatable reads, also called as fuzzy reads. A transaction reads the data twice and finds the data to be different each time because another transaction have modified this data in between two reads. This means the record was not repeatable stable during the transaction. Another one is phantom read. A transaction re-executes the same query. For example, select star from account where balance is less than 100 and finds that the set of rows has changed. New rows appear or some rows are disappear because the another transaction have inserted or deleted the rows that meet the query condition. The phantom is the new row that was not there initially. Okay. So another one is more complex anomalies occur under certain conditions. For example, two transactions, both of them satisfied one condition only because the another one has not committed yet. But it will lead to a violation when both of them commit together. These are beyond the basics but can be solved by strictest isolation. So the conclusion is without proper isolation, concurrent transaction can intermix in a problematic way. The database's job is to prevent these anomalies or at least limit them based on a chosen isolation level. Okay, so isolation level. Let's talk about isolation level now. Isolation levels. Most database systems offers a configurable isolation levels that balances strictness versus performance. Higher the isolation, it provides more protection against anomalies, but at the cost of lower concurrency. So that means more waiting and more blocking start or takes place. The standard ANSI isolation levels are first is read uncommitted. This is the lowest level of isolation where the transaction may see the uncommitted changes made by others. This level allows dirty reads. In practice, few systems are using this except in special cases because the anomalies are severe. Second is read committed. First was read uncommitted. This is read committed. This was the lowest level, that is lowest isolation level. This is the medium isolation level. This is the common default in many databases where each transaction only sees the data which are being committed by other transactions. However, non-repeatable reads can occur. If another transaction have modified this row or updated this row in between two reads and committed between two reads of that row by your transaction, you will see the new data on the second read. Okay, let's discuss the another one, repeatable read. This is the strongest isolation level. When a transaction have read a row once, we'll see the same data on the subsequent reads on that row, even if another transaction commits the changes to those rows in the meantime. This prevents non-repeatable reads. However, phantom reads may still occur. New rows might appear if another transaction inserts them and commits. Let's talk about another one, that is a serializable. This is the highest isolation level, which emulates serial execution of transactions. Transactions behave as if they were executed one after another, completely isolating them. This level prevents the phantoms and basically all other anomalies. It is the golden standard of isolation. Serializable isolation ensures full correctness but can require heavy locking or coordination, reducing concurrency significantly. Okay, so now let's discuss how isolation is achieved. Under the hood, databases uses concurrency methods for isolation. Two common techniques are locking, that is pessimistic concurrency. In these, the database may lock the data that is being read or written by a transaction so that other transactions are either wait or prevented from making conflicting changes. So, for example, suppose T1 is writing to the X, it will make the lock, it will use a write lock so that T2 must wait for read or write until T1 is finished. Or else T2 might get an error if the system uses the lock timeouts or deadlock detection. This ensures sequential access to critical section of data which will prevent races. This is about locking, that is pessimistic concurrency. Now second is multi-version concurrency control, which is also called MVCC, optimistic currency. In this, the database keeps the multi-version of the data, for example, old snapshots, to allow readers to see a stable snapshot of the database while the writers update data in the background. This way, the readers don't block the writers or vice versa. Each transaction sees the database as a certain version. When it is time to commit, if there have been conflicting changes, an optimistic concurrency control might abort the transaction. MVCC is used in the systems like Oracle and PostgreSQL to implement isolation levels without heavy locking by allowing the transaction to proceed in parallel and only resolving the conflicts at commit. Overall, isolation ensures that even in the highly concurrent system with many users, each transaction can proceed with the illusion that it is running alone, and the end result will be equivalent to some order of serial execution. This greatly simplifies reasoning about concurrent operations and prevents the host of correctness issues. Okay, so now let's talk about durability. Durability guarantees that once a transaction is committed, its effect will not be lost, even if the system will crash immediately afterwards. In practical terms, durability means the database have safely returned the transaction's data to non-volatile storage, for example, disk, SDD, etc., or replicated it to the other systems, such that a subsequent power loss or hardware failure will not undo the transaction. The data will persist and will be available in the future, which is essential for fault tolerance. In simple terms, if you see a message that your transaction has been committed or your order has been placed successfully, durability ensures that the changes are not just in the memory. They are saved in a way that it will survive resets and crashes. The committed data will still be in the database when the system comes back again. Okay. Think of writing a document. If you will only keep in the memory like notepad and your computer loses the power, you would lose all of your work. But durability is like hitting that save button. The document is now on the disk. Even if the power goes out, you can reopen the file and your changes are intact. In an online shopping context, durability is not just like showing you the order confirmation, but also having recorded that order in the database and maybe send it to a backup server so that even if one server fails, your order is not lost. Okay. So now let's discuss how it has been implemented. Databases ensures durability by using such techniques such as WAL and data replication. Here WAL is write ahead log. We have discussed about this in our previous starting lectures, but let's go into that. What is WAL? It is write ahead log. This is a fundamental technique where any changes a transaction makes are first recorded in the transaction log on stable storage before applied to a main database. The log is append only record of changes. By writing to the log first, the databases can recover from the crash. Or restart, the system can replay the log to redo any committed transaction that were not first applied. Or undo the transaction that were not committed but had some changes in progress. In essence, if the database crashes, it consults the log to decide which transactions to finalize and which to roll back, thereby covering to a consistent state. This log is itself stored into a disk. As a result, once the transaction is committed, its log record is safely on the disk. And the database uses this guarantee that the change is not forgotten. Okay, that was about the WAL. Now we are going to explore replication. We have already discussed about replication in the previous video, but let's do a quick revision. Many databases increase the durability by copying the data to multiple nodes or servers. For example, in distributed databases or cluster databases, when a transaction commits, the data might be replicated to one or multiple servers. If this primary server fails, the replica have the backup. Some system commits the transactions only after at least two or majority of the replicas have the data. This is called a synchronous replication, which ensures that the data truly survives single node failures. Other system uses asynchronous replication, which is faster but risks a tiny window where a recent commit could be lost if the primary fails before sending the data out. Durability is the reason why database uses reliable storage hardware and techniques like journaling. When you configure a database, options like sync to disk on commit or using an SSD with a battery back cache are all about ensuring that once a user is told that a transaction has been committed, the data is really safe. So that was about the replication. Okay, now let's talk about singular node versus distributed transactions. Up to now, we have discussed about transactions mostly in the context of single database on one server. In a single node database, implementing ACID transactions is simply straightforward. In what? In single database on one server, because the database engine has full control over a local set of data. It uses local logs, memory, and disk. All ACID properties can be enforced within that one system. However, modern applications often use distributed databases or microservices where data or workload are spread across multiple nodes or services. Ensuring transactional properties in a distributed context is more challenging and involves a lot of trade-offs. Okay, in that case, let's talk about transactions on a single node. In a single node relational database, like a traditional SQL database on one server, the database engine ensures ACID using the techniques we described. Let's talk about atomicity and durability. We are ensuring atomicity and durability by write ahead logs and crash recovery. If a server crashes on restart, it will use the log to restore its consistent state. Second is consistency. We can achieve consistency via enforcement of constraints at commit time. All checks are done within server. Another one is isolation. We are achieving isolation via lock manager or MVCC within that one database process. All of this operation occurs on the same machine. So there is no network latency or split brain scenario to worry about when coordinating a transaction. Either the transaction commits on that server's disk or it doesn't commit at all. Okay, now let's talk about transaction in distributed database. When transaction needs to span across multiple nodes, say you have a database cluster or a shared database where different pieces of data resides on different servers, maintaining ACID becomes more complex. This is because now the system needs to ensure that all the nodes involved agree on transaction outcome and do so in the presence of communication delays or failures. One common algorithm for this is 2PC or two-phase commit protocol. In this, a coordinating node asks all the participating nodes if they can commit transaction. So this each node will check the constraints, reserves, resources, etc. to say yes or no. Yes means yes to commit and no means abort. Second is commit phase. In this, if all of these nodes voted yes, then this coordinated node will send the commit command to all of these nodes, and each of these node will commit the transactions locally. But in this, if any of the node voted no or faced failure in transaction, then this particular coordinated node will send the command that roll back or abort the commands. And after this, suppose this particular node have done some of the changes, this node, coordinator node, will tell that just undo all the changes which you have executed. So the conclusion is 2PC protocol ensures atomicity across all the nodes. Either every node commits the transaction or every node aborts the transactions. Okay, so now let's talk about real world scenarios. Any system dealing with the critical data can be discussed in terms of asset. For example, inventory management, ticket booking, logging and metrics, ETL or data pipelines. Okay. So in this, preventing two warehouses from selling the last item simultaneously, use a transaction or locking to ensure only one decrement happens. In ticket booking system, we need to ensure that the two customers can't book the same seat on a flight or concert. The system should isolate both the booking transaction so that once a seat is been taken by one transaction, another can't take it before the first is finished. Also, in logging and metrics, even systems like logging events can use the transactions if multiple records must be synced. Though often the logs are just appended, which is naturally atomic in single write. And in this, when moving the data in batches, you might use the transaction to guarantee that all the pieces of data for a batch are loaded or none if there is a failure. So, in system design interviews, understanding when you need transactions and when you can relax them is important. Interviewers may ask something like, would you use NoSQL database or sequential database? Would you use relational database or NoSQL database in this design and why? A good answer might mention if the use case requires a strict consistency, for example, banking or financial, etc., and ACID compliant relational DB is preferred, where if you need massive scalability and can tolerate slight inconsistencies, like for example social media feed, a NoSQL might be chosen for availability and speed with the application handling eventual consistency. Okay, so that's it for today's video. We have discussed what is transaction, ACID properties, atomicity, consistency, isolation, durability in depth with examples, single node versus distributed transactions, real world scenarios. So I hope you have understood all the concepts. If you are still watching this video, then make sure you like this video, Comment your doubts if you have any, and please make sure subscribe to the channel so that it will motivate me to make more videos. Thank you so much for watching.